Let us now consider a simple circuit where various wire samples of different lengths and cross-sectional areas can be investigated. We find that the resistance R of the wire sample varies proportionally with length and inversely proportional with cross-sectional area. Hence, the resistance is proportional to length on area, L on A. And the constant of proportionality, denoted by ρ, represents the resistivity of the material. The units of resistivity are ohm meters. So as I'm showing here, if we work out the units of ρ is Ra on L, resistance in ohms, area in meters squared, divided by meters, and we are left with ohm meters. So those are the units of resistivity. So we define the resistivity ρ of a material at a particular temperature as the resistance of a sample of unit length, meaning 1 meter, and unit cross-sectional area, meaning 1 meter squared. We can also define the conductivity of a material, symbol sigma. And this is defined as the reciprocal of its resistivity. So conductivity is 1 on resistivity. The units are therefore ohms to the minus 1, meter to the minus 1. You must know therefore that resistivity is a property of a material, whereas resistance is a property of a particular object. So for example, if we have two different conductors, both made of copper but having different size and shape, these will have a different R, a different resistance, but the same resistivity and conductivity. The resistance and hence the resistivity of a material is found to vary with temperature. We define the temperature coefficient of resistance, symbol alpha, as the fractional increase in resistance at 0 degrees per unit rise in temperature. Mathematically, this can be written as change in resistance divided by the resistance at 0 degrees R0 all over the change in temperature, delta theta. The units of alpha, the temperature coefficient of resistance, from here we can see that it is simply per Kelvin or per degree centigrade. Since ohms cancel with ohms, so we are left with units of temperature in the denominator. It doesn't matter whether it is in kelvins or in degree centigrade, because here we are talking about a change in temperature. And the change in temperature of 1 Kelvin is equivalent to a change in temperature of 1 degrees centigrade. So what does it mean? Say, for instance, that the temperature coefficient of copper is 4 times 10 to the minus 3 per Kelvin. It means that a copper wire having, say, a resistance of 1 ohm at 0 degrees will therefore have a resistance of 1.004 ohms at 1 degree centigrade, a resistance of 1.008 ohms at 2 degrees centigrade, and so on. So that is the meaning of this number here. It shows us by how much the resistance will increase per unit rise in temperature. The equation can be rearranged further, since the change in resistance can be expressed as R theta minus R naught, meaning the resistance at a temperature theta less the resistance at 0 degrees. Then in the denominator we have R naught, which is the resistance at 0 degrees, and delta theta is the particular temperature theta less 0. So it is simply theta. So if we arrange with our theta subject, we get R naught plus alpha R naught theta, or we can simply write it as R theta is equal to R naught brackets 1 plus alpha theta. And here I'm showing a graph of how resistance varies with temperature for a material having a positive temperature coefficient of resistance. For instance, metals. And this means that the resistance of metals increases with temperature. The increase is linear because, as we will see later, we can arrange the equation in the form y equals mx plus c. On the other hand, other materials can have a negative temperature coefficient of resistance, for instance, semiconductors. And this means that the resistance therefore decreases as the temperature increases. Let us now consider an experiment aimed to determine the temperature coefficient of resistance of a copper wire. We would need a length of wire wound as a coil and placed in a tube filled with oil, which is then inserted in a beaker with water. Paraffin oil ensures better thermal contact with the coil of wire. The temperature is monitored using a thermometer. The experiment simply consists in heating the water beaker. You can simply use an electric hot plate. Its temperature is increased, say, from around 20 degrees room temperature to, say, 70 degrees centigrade, during which the resistance of the wire is noted using an ohmmeter, say at intervals of 5 degrees. We therefore end up with a table of results of temperature and resistance values. From theory, we know that R theta is equal to R naught 1 plus alpha theta. Rearranging a bit the equation by opening the brackets, we end up with this, which clearly shows that if we had to plot a graph of R theta, meaning the resistance at each temperature theta against temperature theta, so R theta on the y-axis against theta on the x-axis, then we should end up with a straight line graph with a y-intercept which is equivalent to R naught. Don't forget that R naught means the resistance of the metal at 0 degrees, and a gradient which is equivalent to alpha R naught. So therefore we can determine alpha simply by dividing the gradient by R naught. Let us now look at a couple of questions.